Dimensional homogeneity is effectively a set of rules that tell us how we can manipulate the units of different variables so that we don't sort of violate physical principles. In the case of multiply and divide, the general rule is that anything goes. So in the case of, let's use torque as an example, if we have some lever arm that's fixed at some point over here, and we apply a force down at the end of it, the torque on this point is going to be the force times by the distance. And if we look at the units, torque is going to have units of Newton meters or foot-pounds, some force times by some distance, and we see that this is exactly the units of the individual units, force and distance. Now in the case of add and subtract, we must have the same units. To illustrate this, if you look at a couple of line segments, maybe we have one segment that is 5 feet and another segment that is 2 feet. If we wanted to add them together, it makes sense that we would get 7 feet. But what doesn't make a lot of sense is if we had a line segment, one was 5 feet, the other was 2 inches, because the units are different, we can't simply add them together and say it's 7 feet. So they have to have the same units when you're adding and subtracting, but in the case of multiply and divide, we see that we can just manipulate the units independently, or just times and divide them together. For equations, the units on the left-hand side have to equal the units on the right-hand side. This is a really useful thing to realize, especially if you're working on a homework problem or an exam problem where you don't necessarily know or you can't recall what the formula is. Oftentimes, just by looking at the units of the provided information, you can get a pretty good idea just by piecing everything together. And it's also a really good way to check your math if you actually are working on a new derivation. You need to make sure that the units work out, otherwise you know you've made a mistake or you've introduced some sort of a non-physical approximation. To illustrate this point, let's look at the formula of the position of a moving object as a function of its velocity and acceleration. So just breaking this down, we can start to understand a lot about the different variables in the process. We know that the position is going to have some unit of length. It could be meters, it could be feet. In this case, we'll just work in SI units. So we know that if the left-hand side of the equation has to equal the right-hand side, and that units added together have to be the same type, we can automatically infer that x naught is also a physical position. If we know that time has units of seconds, we have to figure out that whatever velocity is times by time has to equal units of length. So in this case we can infer that the velocity is merely meters per second, and using the same logic we now have time squared, so we have to infer that the acceleration has units that cancel out. So if we work out the math, then we can see these time units cancel out, and we are left with having meters equals meters plus meters plus meters. Everything is okay with this approach. A couple of other additional points of discussion. Oftentimes we'll encounter some functions that are not just simply multiply and divide. There's a class of functions called transcendental functions, and I will try to spell this out. These are functions such as sine, cosine, log, exponential, and so on and so forth. In these functions, if we're looking at, for example, exp of x, in this case, we could also write this as e to the x. X has to be unitless. Otherwise, we don't really have a way to visualize, for example, if we took e to 10 feet, we don't really know exactly what that means. So in other words, we can't have units in any sort of a transcendental function. That includes a log, trigonomic functions, and others, and so forth. Now, if we're manipulating unit conversions, and if we're going from, let's say, SI to American or English, that involves more or less transferring from, let's say, liters to, I don't know, gallons. In this case, it's a relatively simple approach. You just have to figure out how many liters in a gallon and go about the unit transformation. However, if we are ever converting outside, these are just between two different systems. But if we're ever transitioning between different unit types, for example, if we want to go to mass to volume, we'll be working with something in kilograms to liters. We cannot use unit conversion. In this case here, we would have to use density, which is going to be equal to the mass per volume. And this is going to be a physical property. Now, one of the most commonly used sort of conversion factors that we'll use, not really a conversion factor, but something to translate between different properties, is what we call an equation of state. An equation of state is best known, one of the best known equations of state is the ideal gas law. Physical properties are very important in science and engineering because what they allow us to do is to transfer from different types of units. In this case, we have mass and volume. An equation of state is an equation of state if it relates between pressure, volume, and temperature. And we'll talk a lot more about equations of state later on.